Welcome. In today's lesson, we are going to be talking about the operation rules for matrices, which basically just means what matrices can we add, what matrices can we subtract, what matrices can we multiply together, and what matrices can we multiply by a scalar, and what is the result as far as the dimensions. So for instance, this first one, it's just asking us to add these two matrices together, but it's not asking for what the actual outcome is, just what is the dimensions. And we can always add or subtract matrices as long as they're the same dimensions. 4 rows, 1 column, 4 rows, 1 column. We're going to get out a 4-row, 1-column matrix. So to add or subtract matrices, they must be the same dimensions, and the outcome will be the same. Here, we're trying to subtract two matrices. Now remember, multiplying by a scalar doesn't change the dimensions. So once I distribute the 7 in, it'll still be a 1 by 2. But this is a 2 by 2. And to subtract matrices, they have to be the same dimensions. You cannot add a 1 by 2 to a 2 by 2. So no, that difference is not defined. Okay, we can absolutely multiply by a scalar. That 8's a scalar. And anytime you multiply by a scalar, it does not change the dimensions. It just raises that all the elements inside by a factor of 8. So that's going to be a 1-row, 2-column matrix. Again, not the same size, can't do it. Multiplying by a scalar doesn't change the dimensions, so it'll still be a 1 by a 4. They are the same 2 by 2 matrix added to a 2 by 2 matrix. It is absolutely defined as long as they're the same size. Again, we can actually do this addition. The multiplying the 5 in doesn't change it. And then adding, we get a 1 by 2 because the size of the matrices will not change when you're adding. Again, we can absolutely subtract a 1 by 2 to a 1 by 2. Again, now here, don't worry about all the little fractions. Just say, okay, I have a 2 by 2, I have a 2 by 2, and I'm adding them. Multiplying by the scalar doesn't change this 2 by 2, so that one's absolutely defined because which operations are defined. Again, I'm adding a 2 by 2 to a 2 by 2, that's fine. I'm multiplying a 2 by 2 to a 2 by 2. Now remember, when you're multiplying matrices, what I recommend you do is you think about the dimensions of the matrix. The first one's a 2 by 2, and we're multiplying by a 2 by 2. And in order to multiply matrices, the number of columns in the first one must match the number of rows in the second one, or those two middle numbers must match, and they do. So that's absolutely defined. And absolutely, we can always multiply a matrix by a scalar. Again, here we are just subtracting two matrices of the same size, which we can do, 3 rows, 1 column. Again, does the number of columns, I have 1 column because that first matrix is a 2 by 1. Does the number of columns match the number of rows of the second one? The number of rows is a 1, it's a 1 by 2. And those middle numbers, or the number of columns, does match the number of rows. So yes, it is defined. Again, we can add that. It's going to be a 4 by 1. We cannot add those because they are not the same dimensions. We can absolutely multiply by a scalar. Those are not the same dimensions. 3 by 3, 3 by 3, we can absolutely add those. We can always multiply by a scalar. Okay, is the number of columns, which is 3, the same as the number of rows, which is 3? Yes, it is. 3 columns, 3 rows, it does work. We can absolutely minus a 1 by 2 to a 1 by 2. That'd probably put you all to sleep. 2 by 3, 2 by 3, absolutely. How many columns? We have 2 columns. How many rows? We have 2 rows. Yes, we can multiply that. Again, I emphasize, write down the dimensions. That first one's a 2 by 2. The second one is a 2 by 1. Do the number of columns match the number of rows? Yes, they do. Here we're adding. Those are not the same dimensions, so they do not add. Those are the same dimensions, so they can add. Again, looks like they're the exact same dimensions, so yes. We have 2 columns, 1 row that cannot be multiplied together. 4 elements in each, 1 row, 4 columns. We could absolutely multiply those, 2 columns, 2 rows. And how many columns? 1, 2, 3, 4 columns. How many rows? 1. We cannot multiply that. Again, I want to emphasize that. I almost did it backwards. 1 row by 4 columns is that first matrix. The second matrix is 1 row by 4 columns. And again, the number of columns does not match the number of rows. You cannot multiply that, just like this one up here. Again, 1 row, 2 columns, multiplied by 1 row, 2 columns. We cannot do that because the number of columns in the first one does not match the number of rows in the second one. Okay, now what they're going to do is show you some dimensions. Just realize that down here, this is a dimension. It's a 2 by 2. This is a 2 by 2. Multiplying by a scalar doesn't change it, so we can absolutely add those together, and it's going to be a 2 by 2. Okay, so we're adding a 4 by 4 to a 4 by 4. That's perfectly fine. We're timesing a 3 by 1 by a 2 by 3. The last number, the number of columns, does not match the number of rows, so it doesn't work. We're adding a 2 by 2 to a 2 by 2. That's fine. The number of columns does not match the number of rows, so we cannot do it. Again, this little abbreviation here, that just means it's a 2 by 2 matrix. So again, I'm multiplying by a scalar. Absolutely, that's fine. You can always multiply by a scalar. We're adding a 3 by 3 to a 2 by 3. You cannot do that. The dimensions are not the same. That's not a 2 by 2 minus a 2 by 2. Yep, you can absolutely do that, and it is a 2 by 2. 3 by 3 added to a 3 by 2. Cannot do that. 4 by 1 times a 1 by 2. We can. The number of columns matches the number of rows. That's absolutely possible. We can always multiply by a scalar. We're subtracting a 2 by 4 from a 2 by 4, so that is absolutely fine. 4 by 1 minus a 1 by 3, not the same dimensions, cannot subtract them. Okay, multiplying 4 and 3 do not match. 4 columns, 3 rows do not match. We're subtracting 4 by 1 by a 4 by 1. That's perfectly fine. Timesing by a scalar, that's fine. Adding a 3 by 3 to a 3 by 2 cannot do that. Dimensions are not the same. And we can always multiply by a scalar, and it never changes the size of the matrix when we do so. If you have any questions, please bring them to class.